These are the answers to the Chapter 20 packet, Electrochemistry. Section 20.1, Oxidation States and Oxidation-Reduction Reactions. So the mnemonic device, oil rig, helps us remember that oxidation involves the loss of electrons and reduction involves the gain of electrons. In the reaction between zinc metal and aqueous hydrochloric acid, we have zinc reacting with the H+ ions of hydrochloric acid to produce zinc ions and hydrogen gas. In this reaction, zinc loses electrons, so zinc is being oxidized, and hydrogen gains electrons, so hydrogen is being reduced. For each of the following reactions, we have to decide if they are redox equations or not. If it is redox, we have to figure out who's being oxidized and who's being reduced. So in this first example, the phosphorus is going to have an oxidation number of +3 because chlorine is more electronegative than phosphorus. So chlorine is -1. In water, hydrogen is +1, oxygen is -2. In the phosphorus acid, hydrogen is still +1, oxygen is still -2. And phosphorus is going to be +3 to make the total charge 0. Of course, hydrogen is +1 and chlorine is -1 in HCl. So this reaction has no changes in oxidation number for any elements. This is not a redox reaction. In this next reaction, we have a compound called phosphine. This is pH3. Since phosphorus is more electronegative than hydrogen, phosphorus carries a negative oxidation state. It happens to be -3, and hydrogen is +1. As an element, oxygen has an oxidation state of 0. And in the diphosphorus pentoxide compound, since oxygen is more electronegative than phosphorus, phosphorus carries a positive oxidation state. It happens to be +5, and oxygen is -2. And of course, in water, H is +1 and O is -2. So clearly the phosphorus is changing and the oxygen is changing. So we do have a redox reaction. The phosphorus is being oxidized from -3 to +5, and the oxygen is being reduced from 0 to -2. In this next reaction, we have ammonium bromide. So the ammonium polyatomic ion carries an overall charge of +1. Since hydrogen will be +1 in this case, that forces the nitrogen to be negative, in this case -3. And the bromide ion in ammonium bromide, bromide is -1. Sodium hydroxide, sodium is an alkali metal, so it's going to be +1 in all of its compounds. Again, oxygen -2, hydrogen +1. Sodium is still +1 in the sodium bromide compound, and bromide is -1. Now we have ammonia instead of ammonium, but this still has a -3 oxidation state for nitrogen and +1 for hydrogen. So as you can see in this particular example, this is not a redox reaction because there are no changes in oxidation number for any of the elements. And then finally, in this reaction, we know that bromine and chlorine are elements, so they're going to have oxidation numbers of 0. Water, again, H is +1, O is -2. Now we have, in this HBrO3 compound, so this is bromic acid, H is still +1, but since the bromate ion, oxygen is more electronegative than bromine, bromine's going to have a positive charge, and it turns out to be +5. So clearly the bromine is changing, and of course the chlorine is changing as well. So this is a redox reaction. Bromine is being oxidized from 0 to +5. Chlorine is being reduced from 0 to -1. All right, now on to section 20.2, balancing redox equations. We're going to talk about a method of half reactions so that we can make sure that the electrons gained in a reduction half reaction are equal to the electrons lost in an oxidation half reaction. So we're going to multiply the reduction half reaction by 2 so we can get 2 electrons and have the electrons canceled out. So in this case, we still have a balanced equation, just multiplied everything by 2. When we add these two half reactions together, the electrons cancel out, and we end up with 2 iron 3 plus ions plus a tin 2 plus ion. It produces 2 iron 2 plus ions and a tin 4 plus. The overall charge on both sides of the equation is positive 8. So everything is balanced in terms of atoms and charge. This next example, where we have two half reactions, is a little different in that we have a lot more compounds and elements to worry about. So we have nitrate being reduced to nitrogen monoxides, going from +5 to +2. That's a gain of 3 electrons. And then we have diarsenic trioxide. It's being oxidized to arsenic acid. Arsenic is going from +3 to +5. That would normally be a change of 2 electrons, but since 2 atoms of arsenic are undergoing this change, there's 4 electrons involved. So clearly we have to multiply the reduction half reaction by 4 so we can get 12 electrons. Then we're going to multiply the oxidation reaction by 3 so we can get 12 electrons. And now when we add these reactions together, we have some water on both sides, and we have some H plus ions on both sides. So we're going to write the net amount of H plus ions and water molecules. If we have 15 waters on the left, but we have 8 waters on the right, there should be a net of 7 waters on the left. And if we have 16 H plus ions on the left and 12 H plus ions on the right, we'll have a net of 4 H plus ions on the left. So here is the overall balanced equation, which includes 4 nitrate ions, 4 H plus ions, 7 waters, 3 molecules of diarsenic trioxide, 4 molecules of nitrogen monoxide, and then 6 molecules of the arsenic acid. Everything is balanced in terms of charge and in terms of atom. We have a total charge of 0 on both sides of the equation. All right, in this example, we have to determine who's being oxidized and who's being reduced. Manganese is changing from +7 to +2. So manganese is being reduced, and the carbon is changing from +3 to +4. So carbon is being oxidized. All right, so now we're going to balance the reduction half reaction. This is manganese going from +7 to +2. And we have a process in which we balance the half reaction. First, we're going to balance any elements other than hydrogen and oxygen. In this case, we only have 1 manganese atom on both sides, so that's already done. Now we're going to balance the oxygen atoms by adding water molecules as needed. So in this case, we have 4 oxygen atoms on the left, so we're going to add 4 water molecules on the right. Now we're going to balance the hydrogen atoms by adding H plus ions as needed. In this case, we have 8 hydrogens on the right, so we're going to add 8 H plus ions on the left. Finally, we have to balance the charge by adding electrons as needed. The total charge on the right is +2. The total charge on the left is +7. So we have to add 5 electrons on the left to balance the charge. For our oxidation half reaction, we start with C2O42-, the oxalate ion, and we go to carbon dioxide. We do have to balance the carbon atoms first of all. So we'll put a 2 on the right to take care of the 2 carbons. Now we don't have any difference in oxygen, so the oxygens are balanced. We don't have to worry about adding water molecules or H plus ions, but the total charge on the right is 0, and the total charge on the left is -2. So we have to add 2 electrons on the right to take care of the charge. Before we can add these half reactions together, we will have to multiply the reduction half reaction by 2 to get 10 electrons, and we'll have to multiply the oxidation half reaction by 5 to get 10 electrons. So following these steps, multiplying the half reactions by whatever is needed to make the number of electrons lost equal to the number of electrons gained, then we can add these half reactions together and, if possible, cancel any species that appear on both sides of the equation. So on page 832, they have done this for you. So there are the 2 half reactions that have been multiplied by 2 and 5. Then they have the overall balanced equation. There was nothing to cancel out. There was no extra H plus or water molecule, so everything you see there in the overall balanced equation is correct. And the overall charge is +4 on both sides, and we have the correct number of atoms of each element on both sides. All right, now we have a few examples of redox equations, and we're going to balance them using the half reaction method. Okay, let's start with the reduction half reaction. So nitrate is going to nitrogen dioxide. That's a change from +5 to +4. Nitrogen is already balanced. So as far as oxygen atoms, we do have to get another oxygen atom on the right. So we'll add one water molecule on the right. Now we'll add 2 H plus ions on the left. The total charge on the right is 0. The total charge on the left is +1, so we have to add 1 electron to take care of the charge. On to the oxidation half reaction. So copper is going from 0 to +2. There's no worries about water molecules or H plus ions here, but we do have to add 2 electrons on the right to balance the charge. Before we can add these two half reactions together, we have to multiply the reduction half reaction by 2, and then we add the two half reactions together and cancel out the electrons. So the final answer is 4H plus 2 nitrate ions. We have a single copper atom on the left, and on the right we have 2 molecules of nitrogen dioxide, 2 molecules of water, and 1 copper 2+ ion. All right, our next example, let's write the reduction half reaction. That'll be going bismuth from +5 to +3. We will have to add 3 water molecules on the right. Then we have to add 6 H plus ions on the left. Total charge on the right is +3. Total charge on the left is +5. So we have to add 2 electrons on the left to cancel out, to balance the charge. The oxidation half reaction goes from manganese 2+ to permanganate, so from +2 to +7. We'll add 4 water molecules on the left. We will then add 8 H plus ions on the right. Total charge on the right is +7. Total charge on the left is +2, so we have to add 5 electrons on the right to balance the charge. We will multiply the reduction half reaction by 5 to get 10 electrons. We'll multiply the oxidation half reaction by 2 to get 10 electrons. And when we add the two half reactions together, we'll cancel out any extra species on either side. So for example, we're going to have 30 H pluses on the left in our reduction reaction, and we're going to have 16 H pluses on the right in our oxidation half reaction. So 30 and 16, that's going to be a net of 14 H pluses on the left. In a similar way, we will have 15 waters on the right, but then we'll have 8 waters on the left, so that net difference is 7 waters on the right. So just watch out for when you're multiplying these half reactions by whatever number you need to do, watch out for any species that appear on both sides and only focus on the net amount of those chemicals. All right, on to reaction H. This is permanganate changing to manganese. So that is the reduction half reaction. We will add 4 water molecules on the right. We will add 8 H plus ions on the left. And then finally we'll add 5 electrons on the left to take care of the charge. For the oxidation half reaction, carbon is changing from -2 to +2. We have 1 extra oxygen on the right, so we can balance the oxygen by adding a water molecule on the left. And then we'll have to look at our hydrogens. So we have a total of 6 hydrogens on the left, but only 2 hydrogens on the right. Let's add 4 H pluses, and then finally 4 electrons to take care of the charge. Incidentally, those 4 electrons should make sense. If we are going from -2 to +2 as far as the oxidation state of carbon, then those 4 electrons make sense. All right, Multiply the reduction half reaction by 4 to get 20 electrons. Multiply the oxidation half reaction by 5 to get 20 electrons. And then, again, cancel out the electrons and write the net amount of any H plus ions and water molecules. So in this case, we had 32 H plus ions on the left, and we had 20 H plus ions on the right, so that net difference is 12 H plus ions on the left. As far as the water, we had 16 waters on the right, and we had 5 waters on the left, so that difference is 11 water molecules on the right. All right, moving on to section 20.3. So we're done with oxidation, reduction, and redox reactions. 20.3 is about voltaic cells or galvanic cells. All right, so we're talking about zinc added to copper sulfate. On page 835, you can see a strip of zinc is placed in a solution that contains copper 2+ ions, and over time, there's this reddish-brown buildup of sludge on the surface of the zinc. That's copper metal that's being produced. So in this reaction, the zinc is being oxidized from 0 to +2, and the copper is being reduced from +2 to 0. So that is the overall balanced equation, and you can see it right here. Zinc is being oxidized, copper is being reduced. If we try the reverse reaction, it does not take place because zinc loses electrons more easily than copper. Now this table 4.5 on page 136, back in chapter 4 they talked about oxidation-reduction and the activity series. We don't need an activity series to necessarily prove this. In this chapter we're going to talk about cell potential and voltage. But again, zinc does lose electrons more readily than copper does, so the electrons always flow from the zinc to the copper. In a voltaic or a galvanic cell, the transfer of electrons takes place through an external pathway rather than directly between reactants present in the same vessel. Electrons flowing through a wire and ions moving in solution both constitute an electrical current, and this flow of electrical charge can be used to accomplish electrical work. So another name for a voltaic cell or a galvanic cell is a battery. Two solid metals connected by the external circuit are called electrodes. In a galvanic cell, oxidation always occurs at the anode and reduction occurs at the cathode. To remember this, that the vowels go together, so O and A, oxidation anode, and the consonants go together, R and C, reduction at the cathode. Since over time the zinc is being oxidized, the atoms of the zinc metal are going into solution, becoming aqueous zinc 2+ ions. It should make sense that the mass of the anode, the zinc anode, is going to decrease. On the other hand, as the cathode electrode contains copper, that mass is going to increase because aqueous copper 2+ ions are turned into copper atoms and deposited on the surface. So the anode mass decreases and the cathode mass increases. So the half reaction at the anode is zinc going from 0 to 2+, losing 2 electrons, and the half reaction at the cathode is copper going from +2 to 0, gaining 2 electrons. And the overall reaction, if we add these two half reactions together, would be to cancel out the electrons, and the overall reaction we've already seen before. Here we have a diagram showing us that the zinc electrode is in a zinc sulfate solution. The copper electrode is in a copper sulfate solution. They are connected by a wire, and there is also a salt bridge connecting the two solutions together. So the anode is where oxidation occurs, which happens to be the zinc. The cathode is where reduction occurs, that happens to be the copper. The salt bridge is the area in the middle, and the voltmeter is showing you the potential, the cell potential or the voltage. To draw an arrow to indicate where the electrons are flowing, they're always flowing from the anode to the cathode. So zinc is losing electrons and copper is gaining electrons. For a galvanic cell to work, The solutions in the two half cells must remain electrically neutral, so we use a salt bridge so that the ions can travel through the electrolyte solution from one side to the other. Anions always go toward the anode, cations always go toward the cathode. In the wire, the electrons are always flowing from the anode to the cathode. Remember that electrons are flowing through the wire, electrons are not flowing through the salt bridge. Okay, for these 5 reactions, we have 2 metals we're taking a look at. In one case, it's silver and tin. In the next example, it's aluminum and tin, or copper and tin, or silver and copper, or aluminum and copper. But in each of these 5 reactions, there is an anode and a cathode. Oxidation always occurs at the anode. So in this first example, that would be tin being oxidized. And then reduction occurs at the cathode. Silver is being reduced. In our next example, aluminum is being oxidized and tin is being reduced. In our third example, tin is being oxidized and copper is being reduced. In our fourth example, copper is being oxidized and silver is being reduced. And then finally, aluminum is being oxidized and copper is being reduced. So all of these reactions are favored. They're all spontaneous reactions that do occur. Silver is the only metal in this set that was never oxidized, and aluminum is the only metal that was never reduced. So what does this tell us about the ability of aluminum to lose electrons, or the ability of silver to gain electrons? Well, it appears that aluminum seems to lose electrons most easily, and silver seems to gain electrons most easily. So will aluminum give up its electrons to silver, or will silver give up its electrons to aluminum? Well, the first reaction, aluminum plus silver nitrate, that will occur, but if you put a piece of silver metal in aluminum nitrate solution, nothing would happen. So aluminum is losing electrons, and it loses 3 electrons. Let's multiply the silver by 3. Silver is gaining those 3 electrons, so we have a nice balance there. And again, on the activity series back in chapter 4, you can see that aluminum was in fact higher than silver, so it should make sense that aluminum loses electrons more readily than silver does. Okay, this is section 20.4, cell potentials under standard conditions. So we know that the electrons flow from zinc to copper in the galvanic cell. In general, which electrode has the higher potential energy in a galvanic cell, the anode or the cathode? Well, as it says here on page 838, electrons always flow spontaneously from the anode to the cathode because of a difference in potential energy. The potential energy of electrons is higher in the anode than in the cathode. Thus, the electrons always flow from the anode to the cathode. Now, the difference in potential energy is measured in units of volts. So we call this potential difference either the cell potential, sometimes it's called the electromotive force or EMF, or it's commonly called the voltage of the cell because it's measured in volts. All right, so we know that the cell potential can be measured for a galvanic cell, and the sign of this is always positive. So for any galvanic cell, if there is electrons flowing from one metal to the other, that would be a positive cell potential. Standard conditions are the following: 25 degrees Celsius, 1 atmosphere of pressure if there are any gases, and all of the aqueous species in solution have concentrations of 1 mole per liter. For the zinc-copper galvanic cell, which was mentioned in the last section, the cell potential, or the voltage, was 1.10. Now, by convention, each electrode is chosen to write a half reaction. So we can write a half reaction as a reduction. These are called standard reduction potentials, and you can find them in a table in chapter 20 as well as in the appendix in the back of the book. All right, moving on. On page 839, equation 20.8 looks like this. We have the cell potential, which is equal to the half reaction at the cathode minus the half reaction at the anode. So because all of these are written as reductions, when you change a reduction to an oxidation, you change the sign. That's why that minus sign is present in the equation. It is not possible to measure the standard reduction potential for a half reaction directly. The reference half reaction is the reduction of hydrogen ions to hydrogen gas under standard conditions, and this is assigned a standard reduction potential of exactly 0 volts. So what they might do is they might set up a cell involving lead or aluminum or magnesium and compare it to hydrogen. And since hydrogen is defined as 0, they can calculate the potential of any other metal. All right, in this particular series, we have zinc being compared to hydrogen. So the voltage is 0.76. That means that the reduction potential for zinc is actually negative 0.76 volts. Anyway, the reaction that's occurring at the anode is oxidation. So it's the oxidation of zinc from 0 to +2. And the reduction at the cathode is the reduction of hydrogen from +1 to 0. In the galvanic cell, the nitrate ions in the salt bridge are going to migrate toward the anode because, again, anions go toward the anode. And the sodium ions, the cations, would go toward the cathode. Well, instead of using sodium nitrate, if we had used potassium sulfate in the salt bridge, then still the cations, the potassium ions, would go toward the cathode, and the sulfate, the anions, would go toward the anode. Remember that ions travel through the salt bridge, electrons do not travel through the salt bridge, electrons travel through the wire. And again, you can find a table of standard reduction potentials on page 841 in chapter 20, as well as a more complete list in the back of your textbook on page 1064. All right, we learned way back in chapter 5 with thermochemistry, and then more recently with chapter 19 with thermodynamics, that when you take a reaction and you multiply each and every coefficient by n, you would multiply the value of delta H or delta S by that same number. However, the standard reduction potentials are not going to be multiplied by that value. They are intensive properties. So if for some reason we have to multiply a redox equation or a half reaction by n, the cell potential is not multiplied by n. And you can see this on the page 840 example here. We have 10 zinc 2 plus ions plus 20 electrons go to 10 zinc atoms, but still the reduction potential is negative 0.76. So we did not multiply that voltage by 10. All right, now we have 4 half reactions. Again, these are all reductions. And we have to come up with the standard cell potential for each of the following reactions. Our first example involves silver and copper. Now we're going to have to flip one of these half reactions around, since you can't have 2 oxidations and you can't have 2 reductions. So one of these is going to have to get flipped to turn it from a reduction to an oxidation. So we have our silver and our copper half reaction. We're going to take that silver half reaction and we're going to multiply it by 2. However, we do not multiply the voltage by 2. Then we're going to reverse the copper half reaction, and when we do, the cell potential changes from positive 0.34 to negative 0.34. Now when we add these 2 half reactions together, the electrons will cancel out and we'll get the exact redox reaction that's listed in the table. The voltage would be positive 0.8 plus negative 0.34. So the overall cell potential is 0.46 volts. Now for the aluminum tin reaction, we're going to have to take the aluminum reaction and reverse it and multiply it by 2 to get 6 electrons. That did not change the magnitude of the voltage. Reversing it did change the sign, so now we have positive 1.66 volts, but multiplying by 2 did not change the voltage. For the tin half reaction, we're not going to reverse it, but we are going to multiply it by 3 so we can get 6 electrons. Notice that we still have a voltage of negative 0.14, so multiplying by 3 did not change that voltage. The electrons cancel out, and we get an overall voltage of 1.66 plus negative 0.14, so 1.52 volts. Now we have 4 half reactions, and this question is asking us to write a balanced net ionic equation for the redox reaction that would generate the largest value for the cell potential. So if we take the silver reaction, which has a voltage of 0.80 volts, and we take the aluminum half reaction and reverse it so we can get a positive 1.66, that should give us 2.46 volts. And that's the largest value for the cell potential we could generate from these four half reactions. So silver and aluminum are going to be chosen. We're going to reverse the aluminum half reaction, so now we get that positive 1.66 volts. We multiply the silver half reaction by 3, but this does not change the voltage, so it's still 0.8 volts. There's our overall reaction, and again, 2.46 is the cell potential. Now we have chromium and nickel. These both have negative values. We have to generate a galvanic cell for chromium and nickel. So which one of these reactions are we going to reverse if we need the cell potential to be positive? Well, hopefully you can see that we have to reverse the chromium half reaction, and that's going to occur at the anode. So switching the chromium reaction around, now we have positive 0.74 volts. We will have to multiply this by 2, but that still gives us a voltage of 0.74. Then we have the nickel reaction, which we multiply by 3. Does not change the voltage, so we still have negative 0.28 volts. We add those numbers together, so 0.74 and negative 0.28. The overall cell potential is 0.46 volts. So oxidation occurs at the anode, reduction at the cathode, and the cell potential of any galvanic cell is always positive. All right, in this particular question, we have two half reactions. We've got to look on page 1064 to find them. We have to decide which of these is going to be reversed so we can get a positive cell potential. So starting with the first example, we have permanganate and manganese 2+, and iron 3+ and iron 2+. Let's go find those half reactions on page 1064. So these are the half reactions that we have to work with. Hopefully you can see that we are not going to reverse the reduction half reaction because that gives us right now a positive 1.51 volts. We can reverse the iron half reaction and still have a positive cell potential overall when we add those numbers together. So there's the manganese reaction. We did have to multiply the iron reaction by 5 and reverse it. So now we get negative 0.771 volts for the oxidation half reaction. When we add them together, the electrons cancel out, and the voltage, the cell potential, is 0.739 volts. In our next example, one half reaction involves nitrate and nitrogen monoxide. The other half reaction involves copper and copper 2+. Which one are we going to reverse? Well, in order to keep this cell potential positive, we're going to reverse the copper reaction and leave the nitrate-nitrogen reaction the way it is. As far as the electrons, to get them to cancel out, let's multiply the nitrate reaction by 2. So we still have 0.96 volts for that. Let's reverse and multiply by 3 the copper reaction. So now we have negative 0.337. Add these two voltages together, and we get 0.623 volts. And obviously all the reactants and products are still there, but the electrons cancel out. All right, moving on to the next example. We have aluminum and we have hydrogen. Remember that the hydrogen half cell is defined as 0. So it's pretty easy to decide which reaction we have to reverse. We're going to flip the aluminum reaction around. We're also going to multiply it by 2 so we can get 6 electrons. Then we leave the hydrogen reaction alone except for multiplying it by 3 to get the electrons to cancel out. So we have 1.66 volts, and our overall reaction involves 2 aluminums, 6 H+, and it produces 2 aluminum ions and 3 molecules of hydrogen. All right, our next section, 20.5, free energy and redox reactions. So the equation on page 845 is that the cell potential equals the reduction process minus the oxidation process. Since all of the half reactions in the table are written as reductions, the one that you flip becomes an oxidation process, and then of course you change the sign. A positive value for the potential for any redox equation indicates that the process is spontaneous or thermodynamically favored. And if you have a negative cell potential, it means the process is not thermodynamically favored. So we have to decide in each of these four redox reactions, what is the potential and is the reaction favored or not? Our first example involves silver and aluminum. These are the half reactions on page 1064 that are relevant to this redox reaction. Well, silver needs to be reversed to get the silver plus on the product side. We also have to multiply that reaction by 3, so we get a voltage of negative 0.8 for that half reaction. The aluminum is not changed. The electrons cancel out, but the overall cell potential is negative 2.46 volts, so this reaction, as written, is not favored. Recall that earlier in the packet, the reverse of this reaction had a voltage of 2.46 volts, so it would be favored, but this is the reverse of that reaction. So if it's forward in one direction, if it's favored in one direction, it's going to be not favored in the reverse direction. All right, next example, tin and iron. Here are the half reactions we have to work with from page 1064. To get tin 4 plus on the other side, we're going to have to reverse that equation. So now the voltage becomes negative 0.154. The iron reaction has to be doubled. This does not change the voltage. When we add them together, we get positive 0.617 volts, so that reaction is favored as written. Next example involves calcium and hydrogen. These are the half reactions we have to work with from page 1064. We're going to have to reverse the calcium reaction, so that becomes positive 2.87 volts, and we add them together. 2.87 volts is our answer, and yes, it is favored because the voltage is positive. And then finally we have the sodium and the bromine reaction. So these are the half reactions from page 1064. We have to multiply the sodium half reaction by 2. We have to reverse the bromine reaction. When we add them together, we get an overall voltage of negative 3.775, so that reaction is not favored because the cell potential is negative. On page 847, we have an equation that relates the delta G, the free energy, with the cell potential. In this equation, N is a positive number without units that represents the number of moles of electrons transferred according to the balanced equation for the reaction. On page 847, figure 20.14 shows the relationship between delta G, the cell potential, E, and the equilibrium constant, K. So all these equations are doing are relating these various properties of a reaction together. Since they are related, let's go ahead and see how they are related by taking a look at the zinc-copper galvanic cell from earlier. For the zinc-copper cell, the voltage was 1.10 volts, if you recall, because you have to reverse the zinc reaction. You add the two half reactions together, the electrons cancel out, and you get an overall cell potential of 1.1 volts. Now that we know the voltage, let's calculate delta G using this equation. So we have 2 for the number of moles of electrons transferred. Capital F represents the Faraday constant, which is given to you, 96,485 coulombs per mole. And when you multiply a coulomb times a volt, you get a joule. So we get negative 212,000 joules per mole, or negative 212 kilojoules per mole. And that negative delta G means that the reaction is favored, so does a value of the cell potential being positive. So a negative delta G and a positive cell potential mean the reaction is favored. We would expect the value of K to be greater than 1. Let's go ahead and use this equation. Let's solve for the value of the equilibrium constant K. We know it's going to be favored, so it's product favored. We have to write the delta G we have to use the particular value of R, which has joules attached to it. That's 8.314 joules per mole Kelvin. But since the delta G that I've used is in kilojoules, I had to divide 8.314 by 1,000 so that the kilojoules would match up. When I do this math and I solve for K, I get that K is equal to a rather large number, 1.5 times 10 to the 37 power. Again, that large K is consistent with the fact that the reaction is very strongly product favored. Now we're on to section 20.6, cell potentials under non-standard conditions. So as a galvanic cell is discharged, the concentrations of the ions in solution, originally at 1 mole per liter, will gradually change over time. So as the cell runs, the concentration of the reactants decreases and the concentration of the products increase. This is going to change the voltage of the cell over time. So as the cell runs, the voltage progressively decreases and eventually the cell reaches equilibrium. At that point, the value of the cell potential becomes 0 volts, so like the battery is dead, and the value of delta G becomes 0. We can calculate the value of the cell potential under non-standard conditions. Notice that we have a superscript 0 when the voltage is under standard conditions, and then without that superscript 0, the voltage is under non-standard conditions. This is called the Nernst equation, and you can see it's equal to the cell potential equals the standard cell potential minus the ratio of 0.0592 over n times the logarithm, log base 10 of Q. And this is done at 25 degrees Celsius. Now I have a section of this packet which talks about the Nernst equation. The AP exam does not require students to use the Nernst equation to do calculations involving the cell potential. And the Nernst equation is not included on the list of equations and constants given to students on the exam. So you might think, why are we talking about the Nernst equation if we're not going to use it? Well, you can use it if you want to, if you memorize it. However, another way of dealing with reactions under non-standard conditions is to use a qualitative comparison. So we're going to talk about when Q is equal to 1, or when Q becomes larger than that or smaller than that. So let's take a look at these statements from the AP Chemistry course and exam description. Remember that standard conditions would be when all of the concentrations are 1 molar, but many real systems do not operate at standard conditions. We can use the different concentrations that are happening in the cell to figure out what's going on. The qualitative, notice not quantitative, but qualitative effects of concentration can be understood by considering the cell potential as a driving force toward equilibrium, in that the farther the reaction is from equilibrium, the greater the cell potential. The closer you are to equilibrium, the smaller the cell potential will be. Under standard conditions, the cell potential under standard conditions corresponds to a Q equal to 1. But as the system approaches equilibrium, the magnitude or the absolute value of the cell potential is going to decrease, eventually reaching 0 when Q becomes very, very large, when Q equals K. Any deviation from standard conditions that takes the cell farther away from equilibrium than Q equals 1 will increase the magnitude of the cell potential, higher than standard conditions. But any deviations that will take the cell closer toward equilibrium is going to lower or decrease the magnitude of the cell potential. All right, let's take a look at some examples here. Here we have, with using the Nernst equation, we have delta G of negative 212. We have that rather large K of 1.5 times 10 to the 37, and we have a voltage of 1.1 volts. Eventually, when this cell becomes dead, Q becomes extremely large, and the cell potential and the delta G drop to 0. So, if we take our zinc-copper system and we decide to increase the concentration of the reactants, so for example, now copper's concentration is 10 molar instead of 1 molar. what effect is this going to have on the cell potential? It's not 1.1 volts anymore. It's actually a little bit higher than that. Q is less than 1, which means we are farther away from equilibrium, and therefore the cell potential increases. You can also increase the cell potential by decreasing the concentration of the products. So now zinc's concentration is 0.01 moles per liter. Again, Q becomes less than 1, and the cell potential increases. So either increasing the concentration of the reactants or decreasing the concentration of the products will cause Q to be less than 1, and the cell potential becomes greater than under standard conditions. Okay, now let's take a look at examples where instead of Q becoming less than 1, Q becomes greater than 1. So in these examples, we have increased the concentration of the product. So zinc now has a concentration of 10 molar. Q is 10. The voltage is not 1.10. The voltage actually goes down to 1.07 volts. Another way to make Q larger than 1 is to decrease the concentration of the reactants. So when copper becomes 0.01 molar, our Q is 100, and our voltage drops to 1.04. So earlier we had Q that was less than 1, and the voltage was increasing. Now in these examples, Q is greater than 1, and the voltage decreases. So let's summarize the cell potential under non-standard conditions. Again, this is not using the Nernst equation, but rather talking about Q and whether or not we are closer to equilibrium or farther away. If we increase either the concentration of reactants or we decrease the concentration of the products, this will cause the driving force to increase and the voltage will become greater than under standard conditions. So what happens under those conditions is that Q becomes less than 1 and you are further away from equilibrium than Q equals 1, your voltage becomes greater than the standard voltage. On the other hand, if we decrease the concentration of the reactants or we increase the concentration of products, this is going to decrease the driving force, resulting in a voltage that's less than the standard conditions. So when Q is greater than 1, you are closer to equilibrium than Q equals 1, and your voltage will be less. So Q less than 1, voltage increases. Q greater than 1, voltage decreases. Here we have what looks like a rather strange galvanic cell. So what's so strange about this? This is not copper and zinc. This is not silver and aluminum. This is nickel and nickel. This is called a concentration cell. How can you have nickel in both the cathode and the anode? Well, take a closer look at the concentrations of nickel ions. On the left, in the anode, we have a rather dilute solution of nickel ions. And on the right, in the cathode, we have a more concentrated amount of nickel. So this is on page 852. It's called a concentration cell, and it's a cell based solely on the voltage generated by a difference in the concentration. It consists of a strip of nickel immersed in a dilute solution and a strip of nickel immersed in a concentrated solution. In this concentration cell, oxidation of nickel occurs in the half cell containing the more dilute solution, and reduction of nickel occurs in the half cell with the more concentrated solution. If this galvanic cell had been set up under standard conditions, the concentration of nickel would have been 1 molar in each half cell. Well, you can't generate a cell potential if the two concentrations are equal. The cell potential would have been 0. However, this cell continues to operate until eventually the concentration of nickel in the anode is equal to the concentration of nickel in the cathode. So the overall reaction looks like this. We have a concentrated solution of nickel and a dilute solution of nickel. The Nernst equation can be used to calculate the voltage. The value of N is 2 because we have 2 electrons transferred. The value of Q is equal to 1 times 10 to the negative 3, that's products over reactants. and the value of E when worked out in the Nernst equation is 0.0888 volts. The concentration of nickel in the two half cells will eventually become the same. Q will equal 1, and the value of the cell potential will become 0. Because, again, you can't have a cell potential with nickel if the two concentrations are the same for the same metal. All right, moving on to section 20.8. We skipped 20.7 on batteries. 20.8 deals with corrosion. Corrosion reactions are reactions in which a metal is attacked by some substance and converted into an unwanted compound. Some metals undergo very slow chemical corrosion because a thin coating of an oxide forms on the metal surface, and this protects the underlying metal from further corrosion. Two examples of metals that experience this type of protection are aluminum and magnesium. The rusting of iron requires both oxygen and water, and the process can be accelerated by other factors such as pH, the presence of salts, and stress on the iron. For the rusting of iron, reduction occurs when oxygen goes from 0 to -2. Oxidation occurs when iron goes from 0 to +2. Now we have to multiply the iron half reaction by 2 to get the electrons to cancel out. But those are the reduction and oxidation half reactions. And because we need H+ ions, if you have a pH greater than 9, then there are not enough H+ ions to make it rust. So one way to protect iron is to put it in a basic solution, and it doesn't corrode. You can also cover the iron with a coat of paint, or you can galvanize the iron, which is a thin layer of zinc, and zinc will get oxidized and protect the iron. One method of protecting a metal from corrosion is called cathodic protection, in which another metal is used as a sacrificial anode. So, for example, pieces of magnesium are buried near the iron pipe or a storage tank and then connected by a wire. So in this case, the magnesium is oxidized, and that protects the iron from being oxidized or rusting. All right, on to section 20.9, electrolysis. Galvanic cells are based on spontaneous or favorable reactions, redox reactions. It's also possible for non-spontaneous redox reactions to occur, but we have to use electrical energy to drive them. So for molten sodium chloride, that's NaCl, you can get sodium and chlorine. If you can pump electricity through the molten sodium chloride, you can electrolyze sodium chloride into sodium metal and chlorine gas. Electroplating is another example where electrolysis is used to deposit a thin layer of one metal on another metal to improve beauty or resistance to corrosion. So electroplating involves adding electricity and turning an ion into a metal. The quantity of charge passing through an electrical circuit is measured in units of coulombs. This is abbreviated with the capital letter C, and you can multiply amps or amperes times seconds, and you can get coulombs from that. So 1 amp or 1 ampere is equal to a coulomb per second. Here we have two examples involving calculations with electrolysis. Suppose that molten aluminum chloride undergoes electrolysis with a current of 10 amps. How many grams of aluminum would be produced in 1 hour? So we have to go from hours to minutes to seconds. We have to go from seconds to coulombs, from coulombs to moles of electrons, from moles of electrons to moles of aluminum, and then finally to grams. So 60 minutes times 60 seconds. Now we have 3,600 seconds per hour. Multiplying by 10 amps, that's 10 coulombs per second. Using the Faraday constant to go from coulombs to moles of electrons. There are 3 moles of electrons for every 1 mole of aluminum. That's the valence electrons to convert aluminum ions into aluminum metal. That's a 3-to-1 ratio. And then finally, the periodic table tells us the molar mass of aluminum. So the correct answer, after all of these units are canceled out, is 3.36 grams of aluminum. Now, can we start with grams and end with units of time? Yes, absolutely. How many minutes will it take for 1.75 grams of aluminum to be produced? Let's go from grams to moles, then from moles of aluminum to moles of electrons. Then we go to coulombs, and then to seconds and minutes. So we convert grams to moles, multiply by 3 moles of electrons over 1 mole of aluminum. Use the Faraday constant again to go from moles of electrons to coulombs. We have 10 coulombs per second because of 10 amps. Now we have seconds to minutes, and our answer is 31.3 minutes. So these calculations in this section on electrolysis, you can go from either time to grams of a certain substance, or you can go from grams into time. The key conversion factors involve knowing that 1 amp is equal to a coulomb per second, using the Faraday constant to go from moles of electrons to coulombs or vice versa, and then knowing what the charge on the ion is and figuring out how many electrons are involved in that process. All right, well, this wraps up Chapter 20, Packet on Electrochemistry. I hope that those answers and explanations were helpful. Thanks for watching.